this section. So please choose one person to write down the speaker's name. Sorry. The first is the opponent have to challenge the reporter for the problem. We have 1 minute, please.
Start.
Team Lagrange would like to challenge problem number 4, wind speed.
Reject problem number 4.
Team Lagrange would like to challenge problem number 14, dynamic hydrophobicity. Team Lagrange would like to challenge problem number 7, beat dynamics.
Okay, so the second question is beat dynamics. Please choose one person to write the speaker's name on the report. Thanks.
正我跟你说，日久这样子，然后我们就讲公互相讲慢一点。
Start your presentation.
Greeting everyone, I'm the reporter of team evaluation. I'm going to report number 7, bit dynamics. This is our report is divided into 5 parts: introduction and observation, theory, setup, experiment, and conclusion. First, introduction and observation. This is common sentence. A circular hoop rotates about a vertical diameter. A small bit is allowed to roll in the groove on the inside of the hoop. Investigate the relevance parameters affecting the dynamics of the bit. We have 2 key points. How affects the dynamics of the bit, and second, how affects the equilibrium points of the bit. And this is our observation video. In the beginning, the bit will locate at the lowest points of the hoop, and when the hoop rotates, the bit will climb up until it reaches the equilibrium position. And second, theory. A bit of mass M slide on the hoop of radius r, and the hoop rotating with the angular velocity omega in a constant gravitational field with acceleration g. And the theta means the angle between the axis and the position of the bit. And this is the bit force diagram. And its surface friction and its weight and the viscous force and omega squared r. And we establish new S prime and Y prime axis. Let's take a look at Y prime axis. And n omega squared r sin theta cosine theta minus f minus n3 sin theta equal nr phi double dots. And the phi in this expression is the angle, is this angle, and r is the radius of the bit. And theta dots cross r equals phi dots cross r because they equal to the bit velocity relative to the hoop. And f cross r equal I phi double dots because they all equal because they all equal because they are the same. And these are 3 equations of both. And we conclude 3 equations and substitute I into 2 over phi and r squared. We can get the final equation. Omega squared r sin theta cosine theta minus g sin theta equals 7 over phi theta double dots r. And third, setup. This is our experiment setup. A hoop and a bit inside of this, and also a measuring tape. In order to measure the position of the bead. And the motor under the hood. The max power is 3.9 and the variable resistance in order to change omega batteries. And for experiments. As per Riemann layout, we observe the base equilibrium position of different conditions, and as per Riemann 1, angular velocity, we check by checker and we calculate theta, discover the relationship between angular velocity and hood. As per Riemann 2, Typt's radius. We also calculate theta and discover the hood's radius and theta. And theoretical derivation. For theory, we get the final equation 7/5 theta double dot r minus sin theta times omega square cosine theta minus g/r equal 0. So when the bead remains at the equilibrium position, it doesn't move, so the theta double dot is 0. So we can get sin theta times omega square or cosine theta minus g/r is 0. And after calculated, we can get theta equal r cosine g/r omega square. And how to get theta? When the bead is at L centimeters on the scale, we can the theta is equal L/2r. And how to get the angular velocity of the hook? We place the black dots on the hook like this, and the black dots on the hook will rotate with the hook. So with checking the black dots with checker, we can get the velocity of hook. And the video is the rotational video, and the black dot will rotate at a constant speed around a circle. And we just use checker to check it, and we can get its rotational period, and use 2 pi over t, we can get the omega. And as per Riemann 1, same radius and different angular velocity. The radius of hook is 6 centimeters, and omega is the hook's angular velocity. Theta prime is the angle calculated in theory, and theta is the angle measured in experiments. And this is our data. We have 7 data, and we can obviously observe that when omega increase, the theta and theta prime increase too. And this is a chart of diameter 12 centimeters. And green dots means theta, and red means theta prime. And we can see that the two data is very close to each other, so we can measure that the theory is sure based. Okay, so theta is r cosine g/r omega squared, and we substitute r into 6, so we can get r cosine 163.4 over omega squared. And then radius and different angular velocity. This case is the radius is S centimeters, and this is our data of radius. Let's see, S centimeters, and this is a chart, and also the two data is very close to. We can substitute R into X and get the theta is R cosine 122.5 over omega squared. And experiment 2, close radius. We have 3 different radius of the hoop, and is 6 and 8 and 10 centimeters. And discover the relationship with between hoops with different radius and equilibrium positions. And experiment 2. Same angular velocity and different radius. And we have 2 data. One is omega equal 20.9 and the other is 18.8. And L means the position of the beam. And we can observe that when R increase, the theta and theta prime increase too. And this is our chart of two data, and the 2 data is close to, so we can put omega into substitute omega into 20.9 and get R cosine 2.2 over R, and substitute omega into 18.8 and get the theta is R cosine 2.7 over R. Conclusion. Experiment 1, same radius and different angular velocity. The experimental results is very close to hypothesis. So we will sure that the theta is R cosine G over R omega squared, and because the R is the constant, so we can guess this. And experiment 2, same angular velocity and different radius. Experimental result is very close to the hypothesis, so we can get the theta is R cosine constant value over R. Thank you.
Okay. So now the opponent have 2 minutes.
First question in page 15. What is the unit for a 3.9? Is it watt?
Watts.
Okay, thank you. Next question. How did you take the video? Do you take the video when you are doing an experiment to measure the angle of the beam?
Yes.
Okay. Is it from the side?
No. And we have 2 video, and one is built down and one is on the side to measure the L.
Okay. Next question. How much does your hoop weigh?
It's not important.
Okay. How much does your bead weigh?
It's not important too.
Okay. Next question. Next question. How wide is the hoop? I don't mean the radius. I mean the thickness of the hoop.
0.2 centimeters.
Sorry. The inner thick.
It's
Yes. No. From one side to the other side. Width. The width.
2 centimeters.
Okay. Next question. Did you when you are measuring the angle, did you use the whole video? or do you just take a few frames out of the video?
Yes.
Okay, thank you.
Okay, so we wait 3 minutes.
Honorable jurors and distinguished competitors, I'm Chen Liangyu from Team Lagrangian. Today I'm opposing problem number 7, bead dynamics. This is a problem statement. A circular hoop rotates about a vertical diameter. A small bead is allowed to roll in a groove inside the hoop. Investigate the relevant parameters that affect the dynamics of the bead. So I think the focus for this problem should be the dynamics of the bead and what force will induce this dynamic. Next, a summary of the report. Because the problem statement has said to investigate the dynamics of the bead, but they only investigate the equilibrium state of the bead. So we think that they misunderstood the problem statement. And in their theory part, they use Newton's law and also consider the rolling of the bead. And in the experiments, they did experiments on the equilibrium states of the bead, and also they changed the hoop radius and the angular velocity at which the hoop is rotating. Moving on to the pros and cons of the report. First of all, they got a very good time management. Next, their presentation was very well made and easy to read. Next, they provided intuitive explanation for their experiment results. And they also considered the rolling of the bead during their theory. However, they did not have any error bars and error analysis. and they did not explanation. They did not provide explanation for their deviation in the experiment data. And the next is their tracking method is quite error prone. And also they neglected air resistance. And they don't have any explanation for their modeling of friction. And as mentioned before, they did not investigate the dynamics of the bead, but they only investigate the equilibrium state. And also, they did not think. They neglected the weight of the hoop and the bead. So these are some points that we can discuss later. First of all, is what dynamics can be explored. Next, effects of air resistance on the motion of the bead, and also the friction modeling. And also, I think the moment of inertia at which of the whole device will affect the motor's spinning, and the rolling of the bead we can discuss further. And for experiment part, I would like to get some further discussion about the video taking method and some distortion correction, and also other hoop parameters we can discuss. And the release method of the bead can also be discussed. Next, I would like to discuss something about the width of the hoop. So this is my presentation. We can move on to our discussion. So the first question: have you, for the dynamic part, do you have the video from the start, when you start to rotate the motor? Okay, so have you ever tried to analyze the first part of the video from what's at the bottom?
Yes.
And so you mean that you have analyzed the
No, we don't analyze the start parts.
Okay, so you don't think that the starting part is important?
Because we don't have that equipment to take a video of the start, so we can do the experiments.
Okay, so I think the start part is still important because that's kind of the dynamic of the bead. So one suggestion I can make is that you can use a smaller camera, for example a dash cam, and attach it to the top of the hoop.
We know because we don't have money to buy the camera to take a picture.
And also you can only use half of the hoop because in your experiment data, as you shown, you didn't exceed a theta larger than half of pi. So I think you can just use half of the hoop, the lower semicircle, and you can film it from the top without getting blocked. Okay, so the next thing is the friction modeling. As in your report, you have not mentioned what model of friction you use. Is it static and kinetic friction?
We use find double dots over R to substitute.
Okay, so I just want to verify one point. This is the bead is rolling, right? Yes. It's rolling on. Okay, so does this friction this friction is the cause for this rolling, right?
Yes.
Okay, and how do you define phi? I just want to clarify this. What is your definition for phi?
Phi is the beam rotational angle.
Okay, Next thing is I want to talk about the initial condition and the release method of the bead. In your experiment, you start from putting the bead at the lowest end of, at the bottom of the hoop, correct? What if you release it from for example, from here?
It's the same.
But I think maybe there's already a gravitational potential. Maybe the hoop will exhibit some sort of dynamic, for example, swinging back and forth.
No, it will remain as the equilibrium position being moved like this.
Okay, but I think before the equilibrium takes place, it will swing, and that's dynamics, and I think that is important as the problem statement has clearly stated that you should be investigating the dynamics of the bead. Okay, moving on to the next thing. The reason why I asked you about the weight and the weight of the hoop and the bead is because that it looks like your hoop is quite light. It is 3D printed. Okay, so because you mentioned that you use a potentiometer to control the voltage that is going into that motor. So I think that is kind of like controlling the total power that the motor is getting. So when your bead is moving, when the bead have moved up here, it will change the whole moment of inertia of your whole setup. So I think that will affect the rotational, the angular velocity at which the whole device is rotating.
I check the CDA. That's you say.
Okay. Alright. The next thing is about the width of the hoop. As I have asked you about the width of the hoop, because when you are at the bottom, sorry, may I ask another question first? In your hoop, is it? Let me draw it. Does your track look like this from the side, or is it like this? Okay, so I think now we have clarified something. Is that the initial position must be in the center. Do you agree with that?
Yes.
So why do you think? That in this condition, it's pretty much like the bottom of your potential energy chart. So why do you think the motion will start?
Because it has a little tilt, so you can go up and you can come out.
Yes, is this thing is it a semicircle?
Yes.
Okay, so if it's tilted, and let's say it's tilted like this. So when your bead is here, it's at the lowest point of the semicircle. But when your bead is here, it's still at the lowest bit of the curve.
But the motor is
Oh, so do you mean your hoop is decentered? Okay. So do you think that if the motor is not decentered, it's perfectly in the center, will the motion start? Do you think will the motion start if the motor is perfectly centered? Okay. The next thing is, do you think that, because in your theory you are considering the hoop to be a two-dimensional thing, right? It's just a circle.
Yes.
Yeah, but as you can see, the hoop has a width. So do you think that this bead will move, for example, in this direction, like up? That's coming out of that direction is coming out of this. Do you think that it will move like this?
Yes.
Okay, so I think you can also analyze that because, for example, in your experiment setup page, sorry, the one with, yeah, as you can see, you have a width here. So I think you can track it, the width, and sorry, is this picture in this picture is a motor spinning?
No.
But the bead here is not centered.
Yes, it's in the center. Sorry, I think.
Excuse me? But it definitely looks like it's not in the center.
Could you repeat again?
I mean the center of this direction.
Oh, I think it will.
Yeah. So if this is the case, I think one potential cause for the motion to start is like this. When you're looking from the top of the.
Okay, time is up.
So
So you're.
so for my summary, first of all we have discussed about in this discussion we have mostly discussed about the dynamics of the bead, and more precisely we discussed about the starting of the motion, and also we have clarified some points about their friction model, and I also mentioned the reason for me to ask about the weight of the hoop and the bead, and also I have made some suggestions about the improvement of the video taking method, and also suggested other ways to release the bead from other angles of, for example, release it from another angle, and that's my summary.
Okay. So based on the reviewer, question to reporter and opponent.
Okay, so first I want to ask both sides, like, how do you think the initial condition, what does the start of the motion look like in your imagination?
In my imagination, the hoop will, for example, this is the width of the hoop. The bead will move slightly to the side and then go up. But the going up, in this time it might like do this circle thing.
Oh, okay. Then what about you?
The same as me.
Okay, but then do you both agree that if we have a width that is fixed just right to fit the bead, then the friction that it creates would also, if we want to fix the bead like right inside, so the z-axis, so the z-axis wouldn't have any effect on the motion, then the friction that it creates would also affect the whole motion, right?
Yes.
Yes.
Okay, then next question. Why do you think the whole motion will start?
I think the whole motion will start is because the asymmetry of the system.
Okay, then I also want to ask in both sides. In your imagination, how would the dynamics of the trend? How would the trend of the dynamics go? Like, how would the trend go? Like maybe the potential energy or.
So sorry, what do you mean by trend?
How would the dynamics of the bead change?
I think the dynamics of the bead will first of all, I think the dynamics of the beat, for example, at the bottom when it's starting, this will be affected by the angular acceleration of the motor.
The speed will
in your opinion, why do you think the weight of the hoop and the bead would affect, and how would it affect?
Because the bead will move, right? So it will change the moment of inertia of this rotating device. Now we're feeding a constant, let's assume it's a constant power into the motor. So the angular velocity will be affected. So this will be, some, in my imagination, some dynamics will be a result of this.
Okay, then after hearing his explanation, do you agree that we should also consider the hoop and the weight of the hoop? And
Okay, time is up. It's 2 minutes break. Okay. So the viewer take the floor.
Honorable chairs, fellow debaters, and most distinguished guests, from Team H105. And so, in conclusion, the whole I don't think I'll have to say the question again. But in my opinion, what we have to discuss right here, the main point is absolutely the dynamics of
Please
the
take
dynamics of the beat. And
There's the problem
and
in
the-
seeing there.
Please.
It's not the connection bit. Can we switch to the sides?
This side? Can we switch to our record to that side?
Okay.
As I will continue, I think key point we're discussing here is the dynamics of the beat, and and we'll summarize the reporters first. So they have a clear observation and setup for their report, and they also have a really clear methods of how they're using how they're investigating the parameters that they chose. However, we think that more parameters could be discussed in the future. For example, the width of the hoop and maybe the materials of the hoop, because different materials create different amount of friction, and I think that would affect the dynamics of the bead. And then they also have a conclusion, which is that the angular velocity changes how the equivalent point is. But they, to be honest, they didn't quantify this accuracy or like how exactly they did there's no specific number data. And they have really clear for the reporters, they have really clear measurements, and they also have angular. They also have a clear conclusion, but they also lack some physical explanations, which is like why they're using these equations, and then why there are some deviations in their report. Okay, and points for the opponent, they have really short questions and really clear short questions, and they really state the important points that should be considered. However, they gave some very practical suggestions, but they lack some consideration. For example, he said that about you can maybe cut the hoop and fill from the top, but you can't really assure that the bead wouldn't exceed the hoop at the nor know that it would exceed it before the experiment. That is after their data of experiments. Okay, and then starting the clash, there's pretty much so one important part, because we're discussing the part of dynamics, and the change of dynamics is also really important in this problem. So both the reporter said that they didn't consider it because the lack of experiment materials. However, the opponent thinks that the rotation part should be defined, and it's very important. And we agree with the opponent that the starting point is also important, as it is the most complicated part of this movement. But however, we think that there are some but however, we think that we also think that we should consider more energy loss. Okay, and then the next one is clash of the width. The reporter agreed with the opponent, so we also agree with the opponent that we have to fix the width. But as I have just said in my questions, I don't think there are some after we fix the width, then we will also have to consider more friction. And some width point is I don't think the opponent have mentioned much about the energy loss, and I think
Okay.
that's
Thanks. So, final part to conclude with us for the recording.
And discussion, and the top part should be removed due to the angle not exceeding pi over to the reporter agrees, since it may provide another shooting angle. With the friction force affecting the bead, if the width of the hoop was perfectly fixed, yes, and that should be taken into account. However, we can minimize the friction by changing the texture of the hoop. And review. More parameters such as the inertia of the whole system could be considered in the future experiments. And further area analysis could be conducted. And the start of hoop rotation to potentially affecting the whole sense.
Okay. So it's time to our jury for speakers. Please.
I have a question for three teams, and so for the reporter. So can you show your experimental setup? The question for the reporter and for the other two teams are slightly different, but essentially the same. Okay. So for the reporter, I want to ask your opinion about your own setup. Is there anything that you can improve without costing too much? Okay, and of course, kind of the same problem. So I want to comment on his setup, whether if any immediate improvement that can be done. Okay.
We think that you can use power supply to instead of the battery and variable resistance to change the omega.
So I think basically the width, like we have just discussed, could be improved to make it smaller, so there won't be a movement in sideways, and then also maybe the power supplies, because we don't know if the power, as it's not because batteries, the electricity might the power might not be stable as it may be different devices, and I think that can be improved.
I think first of all the battery will the voltage and the output power will drop over time. So I think they should use power supply for the supply of for the power, and also the motor in this. I think this is a DC motor, and I think they can replace it with an AC motor. A DC motor has typically a less stable angular rotation speed at lower speed.
Okay, please. Wen老师.
Just a short question. Can you turn to page 28? Let's see omega, the top line of right. You must have learned significant digit, right? Significant digits. You know how that is? You have too many decimal points. This should not be the case. Okay. And another short question. From your setup, it seems to me that the groove is flat, not a curved one. Right? The groove, inside the hook, the loop.
Is a curve.
You sure it's I'm not testing you, but it looks like it's a flat surface inside the loop. No, that's why even the hook doesn't rotate, the bead can move around. It looks to me it's a flat surface. It's not but anyway, it's just a minor point.
Okay, any questions for Roger? Please.
How do you make sure the feed will go one side? Because your measuring pad only half, right? How do you control that it only goes this way, not that?
We don't want to share that the feed will go this way or that way. We just measure how high will is reached.
Okay, any more questions? Roger? Okay. So, Jerry, can show the scoring board, please. 第二种 speed。So the first scoring is for the reporter is 6, 5, 4, 5, 6, 5. Then the next for the opponent is 7, 6, 9, 7, 8, and 8. The final for the reviewers is 7, 6, 8, 8, 7, and 7. Thank you for this section. Okay, so let's start the second stage of this visit prize. So the opponent team H105, please judge one question.
We would like to challenge the question number 9, light whisker.
We reject the challenge.
We would like to challenge the question number 17, hand helicopter.
We reject the challenge.
We would like to challenge the question number 2, circling magnet.
We reject the challenge.
We would like to challenge the question number 4, wind speed.
We reject the challenge.
开放第3题，要这样。 第15题，更正，开放第15题。哎，第15题本来就有啊。上面本来没有，现在新来出现。因为他们有小题从下面往上看。
那个重新开放是什么意思？
就是当小于5题的时候，然后会从下面开始往上开放，所以现在15是开放。
We would like to change the question number 15. Rebounding capsule.
We accept the challenge.
Speakers have to write on paper.所以它的小于是小于
它是等于就是小于100。
可是如果这边有2个，是2个题。
2个一起。过了，然后9它刚刚
27、20都被裁掉。
所以这里剩下5、6、12、12。
所以要补到
同一场比过的也要删掉。
所以
Okay, you can
Honorable
start.
juries and distinguished competitors, I'm Zheng Boyuan from Team Lagrangian, and I'm going to report problem number 15, rebounding capsule. This is the problem statement. A spherical ball dropped onto a hard surface will never rebound to the release height, even if it has an initial spin. A capsule-shaped object, on the other hand, may exceed the initial height. Investigate this phenomenon. And the definition of capsule shape is a cylinder with hemispherical ends. There are some key questions. How does initial transitional and angular velocity affect the bounce? And when does the capsule bounce higher than its original height? And what's the angle limitation when the capsule collide? And how does friction affect the motion, and how does other parameters affect the motion? And this is the motion observation. From the video, we can see that the second bounce is higher than the first one. And this is our table contents. This is experiment setup. We use 2 ping pong balls and a plastic tube to build up our capsule. The total mass is 6.9 grams, and the radius of the ping pong ball is 2 centimeters. And the rotational inertia is 1.46 mr squared. The definition of theta is the middle line of the capsule to the right side, and the range is from 0 to pi. We did the experiment above a glass pan and used camera to record the motion, and we put the video into tracker to analyze the trajectories, and we can find out the contact angle, omega, and the velocity at different axes. When the capsule hit the surface, the velocity and angular velocity will change, and we define the velocity up is positive and omega clockwise is positive. We have 2 equations, conservation of energy and conservation of angular momentum, and there are only 2 variables. It's delta vertical velocity and delta omega. And by those 2 equations, we can get the delta Vy and delta omega. And this is a trajectory, and with no initial spin. We track 2 points. One is the center of the ball, and one is the center of the mass. And we can see that after the capsule hit the surface, it gets angular velocity, so it bounces lower because energy is transferred to the angular. And this is with initial spin. We give it initial angular velocity, and after a collision, the angular velocity becomes smaller, and the capsule can bounce higher. And we want to know if it can exceed the initial height, so we reform the equation to this, and at the left side is minus delta Vy over Vy, and this becomes a function of theta and r omega over Vy. In most conditions, Vy is negative when the capsule hit the ground, so when that is smaller, is negative, that doesn't happen at the first bounce. And when that is between 0 and 1, the capsule is still going down, and it will bounce again right away. And if this number is over 2, that means the capsule will bounce higher. So we draw that theoretical surface in 3 dimensions, and we use theta r omega over Vy and minus delta Vy over Vy to be the 3 axes. And we put our experimental data on it, and it's quite fit. And we can also draw when minus delta Vy over Vy is equal to 2, that means when the surface, when the green and red one is over that blue plane, when this condition, the capsule will bounce higher. However, there are some angle limitation. For example, if we are thinking, if our capsule can hit the surface like this, and we have to move the time backward and to see, the bottom of the capsule has already gone beneath the surface. So this is what it will really happen when they collide. And there are 2 kinds of angle limitation. One is when capsule hit like this at the right or at the left. So there are two angle limitation. And as we can see, when the omega becomes bigger, the two lines are going to converge at 90 degrees. And we can draw that in the 3 dimension, so we can see that this blocks out the impossible condition. Now, we observe the theoretical plane. Those two axes are the theta and the r omega over v1. And we can see it is point symmetry, because when capsule hit at right or left, the motion should be likely. And we can draw the line of contact angle is equal to 90 degrees. When this happens, there is no transfer energy from the linear to the angular. So it will just get to the initial height. And when the contact angle is big, we need more r omega over v1 because too much energy is transferred to angular velocity. And now we fix the theta same, we can see if the omega is bigger, the capsule can bounce higher. And if we fix the r omega same, we can see in different r omega, we can see the higher r omega it is, the theta contact angle is going to be flatter when the capsule can get to the higher height. And from the video, we can see that the higher omega is, the contact angle moves to the maximum height occurs when contact angle moves to the 0. And this, we also have to consider the angle limitation. And we can differentiate this equation to get the extra modes. And this arc cosine does not always occur in positive. When it's a negative, this does not exist. And now we want to find out at what omega the capsule will definitely bounce higher at the right angle. And there are two kinds of condition. First, when the blue one means the capsule does not bounce higher, and the red one is the angle limitation, and the orange one means it will bounce higher. And we solve that equation equals to 2 and get this plane, and we solve for, we set the theta equals to 0, and we set that red, we solve that red point. If that is below 1, we don't have to consider the bounce limitation. So this omega is what we want, and this is the one we solve of our experiment. And however, if that result is over 1, that means the omega we want to find is at this point. And so we have to find the intersection of 3 color surface. Now, I'm going to talk about the effects of the friction on delta omega. There are two ways. One is to find the Vx and calculate the impulse, and then we can know the delta omega. The other one is to find out the impulse caused by normal force, and we can times a connected friction coefficient, and we can get a frictional impulse. However, the second one is not, we cannot use that because from one research we can see that in different collision ways, the direction of friction is not always the same, and it is not proportional to the impulse done by normal force. So we have to find out delta omega by delta Vx. And first we have to find out the direction of free friction. There are three things we have to consider. The first one is the horizontal velocity of the center of mass. And second one is the velocity caused by the angular velocity. And third one is the velocity caused by when the capsule collides. And after combine those, we can find out the velocity of this point to the contact point velocity. And in these graphs, it shows that the x-axis is the negative of the relative velocity of the contact points, and the y-axis is the delta Vx. And from the experimental data, we can know that we predict the direction right. And the red icons is the experimental data, and the blue one is the theory that we do not consider the friction. And the green cross means it is the things that after we consider friction, and we can see the percentage error drop a lot. So we can know that the friction has the it's right that we can use delta Vx to find the impulse caused by friction, and know is how friction changes delta omega. This is conclusion. When the contact angle is fixed, minus delta Vy over Vy increase with the angular velocity. And when angular velocity is increased, the maximum of the minus delta Vy over Vy moves closer to 0, which means it can bounce higher. And the angle boundary depends on R omega over Vy. The greater that is, the range will be smaller, and the contact angle will be limited to approach 90 degrees. And to solve the intersection of the surface and the limitation, we can solve that equation equals to 2, and we can get the crucial omega of the capsule that will definitely bounce higher at the side. And by delta Vx, we can know the impulse caused by the friction and predict the delta omega, which is the motion of the capsule more successfully. This is my report. Thank you, everyone.
Okay. So let's move to the opponent. Have short questions to the opponent.
Does the capsule rotate during the contact with the surface? Does the capsule shape object?
We suppose that the contact is instant time, in a just instant. Yes. So we do not consider the.
Then how short is it? How long is the contact duration? Did you measure it?
That is smaller than the 1/240 seconds.
Okay. Do air resistance change the angular velocity?
Research we focus on the velocity change and angular velocity change at the instant of the collision.
So air resistance, is there any change if there is air resistance?
It is influenced, but the main point we focus on is the velocity change.
Okay. Does the mass loss change during the impact?
Is
there any mass loss during the impact?
Mass
of the
no.
No. How do you measure the inclination when it contacts the surface?
Can you say again?
How do you measure the inclination when the...
We use tracker.
Okay. Did you consider how much spinning speed that it changes into its potential energy?
You mean that what?
How much energy and how much velocity and energy is changed into potential energy during the impact?
The velocity will change into a potential, but that is not in the when it's collision.
刚领不到。
Okay, time for the opponent. You have 4 minutes.
Okay, so I'm the opponent on team H105 and I'm opposing on question number 15. So for the problem, we think that the most important is the capsule shape, and it may exceed the initial height of its releasing. So for the summary of the report, we think that there's many strong points that they have include definition, strong point, and clear limitations. And also graphs are included in the report. However, we think that according to the report, there's too many mathematical calculations, but there's no explanation of every physical meaning behind them. And we think that the experimental data isn't show up in your report. So these are the strong points that include definition, convenient for later discussion, includes theoretical simulation, and therefore we can acknowledge the limitations, and many graphs too easy to comprehend. But for the weak points which we suggest to be changed is that they don't have many real-life experimental data. It's like all putting their imaginations into the theory, but no data we can see. So for the second point is that we didn't see the experimental setup, which we have a question on, and we need much more physical explanation behind the theories. Next, we have this. I want to move on to discussion.
Okay, please.
So for my first question is on page 5. As I can see, your object is not as the problem statement. In the problem statement is a Typt, which is an oval-shaped object, which is capsule-shaped. But as I can see, there's 2 balls attached to each other, which may have a mass distribute. Can you explain?
I think we use the classic 2 to be make the centimeter of the shape of capsule, and the definition of capsule is.
Yeah, but if you have there will be air inside your object, right? And there will be a mass distribute, which the CM is not in the center, at the center of middle.
We use the rotational inertia to fix.
Fix. So you
do the
use the calculate to fix the deviation.
Yes.
So
No.
my suggest is that you might want to try if there's a difference between a Typt or your object which is used. For my second question is that how do you release the object at a certain angle? I didn't see any clip or something that can attach to the side.
You mean the angle release or the?
You release the angle.
We do a lot of experiments in different release angle and to put the experimental data.
How do you measure your releasing angle?
Tracker. We use tracker to track all the
So
motion.
you use your hand to
Yes.
to let it go.
Yes.
Okay. So in my imagination, your hand might cause a mass loss, or maybe there's any humidity on your hand, which may change the weight of it and may change maybe the shape, or you give it an extra energy. And on your hand, you cannot have a certain inclination if I want it to be released at 30 degrees.
We think that the mass is too small.
So my suggestion is that maybe you can use something to attach it at a certain angle. And for my third question is that how do you consider the friction and normal force during the rotation within the context with the surface?
We can use tracker to know the change in the horizontal velocity, so we can know the impulse caused by the friction. And from the thesis, as I told, the direction of the friction when it collides is not always the same, and it is not in proportional to the normal force.
So
impulse.
in my imagination of doing this experiment,
Yes.
the capsule might contact on the surface within a short time, which I assume it to be like 10 milliseconds. But there's already an angular velocity in there, so maybe it rotates during the impact. So it may drop onto the surface with a 20-degree inclination, but bounce off with a 25 degrees inclination. So there might be a difference in the friction and the normal force. So in my opinion, I suggest you to do more research or theory to explain both friction and normal force impact during the inclination. During the contact.
But the influence of that is too small.
And
when we see the video, the change is very small.
Okay, that's it. I want to move on to the next question. So I think that the humidity in the air might change the air resistance.
That is small too, because we focus on the instant time before and after the capsule collide.
Can you prove that it's small enough?
From the trajectory of from that we try we
So
see
you
that
do
it's
it
not.
with many experiments.
We do a lot of experiments.
How many data did you choose?
How did I choose?
How many times did you do this experiment? Within
More
different
than
releasing
100.
angles.
I think with these are the experiments we do.
Yeah,
and we still do a lot.
One of the parameter is that the releasing angle, I think, right?
Yes.
So how
much
data did you do for each releasing angle? I just want a short, simple answer.
But we focus on
I
the
want a
contact
simple
angle.
answer, a number.
We do more than like 30 times.
Okay, 30 times. Does the shape of the capsule change during the contact?
It could change, but it will recover.
So I think that the shape is not capsule. So the air in between, does it change the result in your experiment?
It could change, and we have the number of the elasticity.
How do it change?
How do the shape of the capsule change?
How does the air included in your object changes the experiment within your theory? Because in your theory, you think that it's a capsule shape, right? But it's different to your experiment object.
The definition of that, yeah.
I mean, is there a comparison between your object and your theory?
Comparison meaning what?
Because your object, your experimental object is not as your theory. It's not a capsule shape.
This is a capsule shape.
But there's air inside, so I mean the.
No, but the plastic tube, we use plastic tube to cover that, so that doesn't matter.
Okay.
And we use super glue to make there's no air moving out in it.
In my imagination, there will be difference between your object and capsule shape because the mass distributed in the thing is different. So I would like to move on to the next question. Is there any elasticity of the object surface?
Yes. Of the capsule?
Yes.
Yes.
If there's any elasticity of the object, there will be more than one contact point. How do you consider that in your result?
Because when we do the experiment, we use the gas and we find out the case very high. So
you mean that you didn't consider if there are more than one contact point?
It means
there might be a small area, might be a DM in your.
Yeah, and that is small, and I think doesn't matter. And from the video, we see the contact area is about the same.
Okay, so that is my problem. So I think that the area that it contacted will be more than one contact point. So there might be a difference in the torque.
Yeah, but the impulse will be the same.
In my suggestion, I would say that you might want to consider how big the area and how much the contact duration during your experiment, and make a comparison between your theory.
Yeah, but we use impulse to solve
the
my
next question. I would like to ask is how do you consider your deviation?
Just use percentage error.
So you only did you consider different kind of ways to find out the deviation difference?
We can just do.
So you just use average, right?
This is the average percentage error.
Okay. So on page 27.
Yes.
I would like to ask why is the equation equals to 2 on the right hand side?
Because when that is equals to 2 means when that equals to 2 means the capsule will bounce to the initial heights.
Can I have any physical information?
Because when the capsule hit the surface, it has a Vy which is negative. And if delta Vy is equals to 2 times the negative Vy, which means,
okay, I know.
Yeah, so that means it will like 2 times of that,
okay.
so that will bounce.
So for my next question is, if the angular velocity torque is bigger than the speed for moving forward, will there be any friction that goes forward which accelerates the object? Do you consider that?
And what direction?
So the ball might be rotating.
Yes.
So there will be a torque of the angular velocity.
Yes.
So if the angular velocity torque is bigger than the speed which is going forward, can you explain the friction during the impact?
The friction does parallel to the surface.
Yeah.
So it will cause the angular velocity change and also cause the horizontal.
In my point of view, if the torque make it go backwards is bigger than it's moving forward, the friction should be going forward, right?
It decides on what is the relative velocity of this contact
In
point.
my point of view, there will be there will be an angular velocity moving backwards, right? It is spinning this way.
Yes.
But the object is moving forward.
Yes.
So if the torque of this, like the duration, but is bigger than your velocity, the friction might be going forward. Did you consider that?
Yeah, because we use three things to consider. What is the contact point velocity? First is the horizontal velocity of the center of mass. Second is the that's caused by
And
omega.
just have an explanation of when the friction is going forward, how would it? Only when it's forward. Only when the friction is accelerating your object.
Yes.
But
So
I want an explanation of that.
so
Okay, wait.
That
I'll
was-
move on to my next question. So, what is the energy that is given to the objects to do a vertical bounce?
the kinetic energy just will change to the potential energy and just like
Okay.
this.
How much is the energy exactly?
Okay.
We can
time is-
use the kinetic
time is up.
energy to calculate that.
time is up.
So,
So you have 1 minute.
for the summary, I think that there's too much parameters for to be ignored in the reporter's point of view. He told me that the duration, time of the contact, and the mass loss, and even he released the object in his hand. So that's too much deviation in between the whole experiment. And still, I didn't see much data which can prove that his experiment and data and comparison between his theory and experiment, which I cannot see there's any similar place or different place. And I also want to claim that his object isn't really similar to what the problem statement wants. And for the last, I didn't
Okay,
see
time-
how much
time is-
energy.
Times. So now move on the reviewers to question to propose.
Okay, first of all, good to see both of you. Okay, so let's start. First of all, can you turn your presentation to page 14? I believe it's like the one with no angular velocity. No, 14, not 74. Oh yeah, no initial spin. So you said that the capsule-shaped object had no initial spin when it landed on the surface.
Almost
Yes.
no.
Almost none. Okay, did it land, where is the contact point? No, I mean on the capsule. Where did it land? Did it land on like the side or like
The contact
edge?
angle is 36
Okay.
degrees.
Okay, 36 degrees. Now, question, page 18, please, thank you. You said that the experiment, correct me if I'm wrong, the percentage error is the difference between your theoretical calculations and your experimental data, yes?
Yes.
Okay, so for the opponent, do you think that 12% is a small enough number to consider this experiment as a viable one, a
No,
proper
of
one?
course, first of all, I didn't see how much data he did. So for a 12% error, that's quite a lot.
So you do not think that this experiment is proper
For the
to
theory,
describe this phenomenon?
Yeah.
Okay. Okay, this is a question to both of you. Do you think that when the capsule collides with the surface, is it a total elastic collision or an inelastic collision? Yes. Is it elastic or inelastic? For both of you. Please, if one of you would answer my question.
That is not elastic collision.
So it's an inelastic collision.
Yes, there.
Okay.
I think
Right.
it is an elastical.
Inelastic collision, so that means that you
There will
both
be
think
mass
there will
loss
be
and heat loss. Yes.
energy loss,
Yes.
to be precise. So that you both think that there was energy loss. So did you consider that the okay, let me just follow this real quick. did you consider this? Since I can define this as this is the total energy of the system, right? So this is written as 1/2 mv squared, and this is written as 1/2 I omega squared, and this is written as mgh. Did you consider the changing between these three? Did you?
We consider. Yeah, but the main point we consider is that.
Did you consider that?
We can.
Did you or did you not?
Okay,
Okay,
time
consider
is
the
up.
elastic.
Time is up.
Okay,
Yes.
我没办法考虑，我没办法考虑，我很多我没办法考虑，就把我没办法考虑的东西。
Okay, check the floor.
Okay, so I am from Team Erudition, and this is our reviewer report of the rebounding capsule question number 15. Okay, so first of all, let's check out the outline of reporter's presentation. The observation video was not really that clear. We couldn't really see what happened there, it was too dark, but it did sort of distribute the phenomena. The theory was consist of concise report and physical mathematical formulas that can clearly describe the phenomenon. The setup was concise and easy to create, and it's not very expensive. That is a very good part. The experiment considered a variety of the parameters that are to be discussed, and the conclusion has good typesetting to precisely show the results of the experiment and theory. Now, the pros: concise and good typesetting, as I previously mentioned, and he confidently reported what he discussed. And the cons: the graphs that he presented did not show the R-squared value of the experiment data, which may lead to miscomprehension. He did not consider air resistance, air drag, air friction, none of that, since the capsule itself is actually pretty sensitive to these kind of forces. The experiment actually looks kind of irresponsible with, that's a title right there, just ignore that, with a high percentage error, which is 12% right there, which is rather high if you consider the amount of data that he did, 30 times of experiments. Next, please. For the opponent, fundamental questions were asked, very short, very quick questions. I think that they were all on point. Although important questions were asked, an amount of time was wasted on insignificant questions regarding unimportant matters. Next, please. Okay, so let me just sum up the clash. First of all, the shape is different than that of what the problem statement describes as a capsule, which is a tic-tac thing. The reporter described it as two balls contained within a plastic capsule with two ping pong balls. I agree with the opponent that the object itself should have a consistent mass distribution so that we can properly analyze the center of mass's velocity. Second of all, would there be more than one contact point? And the reporter stated that the area is too small to be considered as a relevant parameter. I agree with the opponent since there is air in the capsule itself, which will be discussed on the next slide, please. How many times did you conduct this experiment? 30 times. More experiments should be conducted regarding this phenomenon, more data should be collected, and since you collected 30 times of data, 12%, that's very high. How does air in the capsule affect the motion? There is no need to consider this. What? The air in the capsule might be pressurized when it gets into contact with the surface, and the volume would change, thus affecting the air drag, air resistance, air friction, and it also changes the contact area within the surface. Now, additional remarks. Very clear and detailed explanation and diagrams from the reporter, props to him. As the capsule is actually very light, the air resistance, drag force, and friction, you need to consider that since the capsule is very easily affected. The opponent does not give the reporter a chance to answer, which results in blunder on both sides, misunderstanding, getting to conclusions too fast. The experiment itself has a rather large error percentage, 12%. The opponent gave clear question props to him. It is unclear if energy conversion was considered or not since he did not answer my question.
Okay.
And that's all.
Time is up. So finally, the reporter has 2 minutes.
Okay, so this is my concluding remarks. And for a mass distribution, we calculated the rotational inertia. So we consider the mass distribution and it will not change. And the rotational inertia just represent the mass distribution. And the inertia, the moment of inertia will not change during the collision. And we wrap a plastic film to make the capsule shape. And from the definition, now we find a capsule which is cylinder with the hemispherical ends, and which means the equipment we made just meets the problem statements, and the Typt name is just is an example for that kind of capsule. And we have sufficient experimental data. And we focus on the impact and the impulse. That is the instant time that the capsule collides, and we focus that and we use impulse to describe all the motion. And because the contact time is very short, and the direction of the friction and the work done by friction is not measurable, so that is why we use impulse to solve this question, solve this problem. And our experimental data shows that those experimental data points is very near our theoretical mathematics. And this is my concluding remarks. Thank you.
Thank you. So it's time to our jurors. Question time.
Question for the reporter. So in the beginning, the statement of the problem said for a spherical object, even with a spin, you will never have this kind of phenomena. So can you tell me what's your idea about why?
Because when it just hit the surface, it only gets the normal force, and there is no additional force that can give more energy into the transitional velocity, so it cannot make the ball to exceed the initial height.
So can you get a conclusion from your study by taking the limit?
What?
By taking the limit of your study, you are studying some Typt form, right? But you can try to change your parameter by the mass, right? to take the limiter to go to the spherical situation, then mathematically you will get something interesting, right?
Yes, maybe.
No, but we didn't think about it.
We didn't.
Okay, thank you.
Okay, any questions?
I have a question for three of you. So I think all of you mentioned the uncertain error. Can you show the slide 14? Yeah. So I want, for example, for reporter to defend your data, whether if you think the 12%, the one with the error, yeah, whether if the 12% is fine, depending on your data, just give specific reason, and yeah, and for the other two teams, you think that if I'm not mistaken, so you think that percentage error 12% is too large, so please give your specific reason, not just your, oh, I feel that it's too big. Yeah, just give the specific reason.
Well, in statistics, we can see we have this thing called the standard deviation, which is represented through mathematical formulas, and you can see that I'm just counting the experimental data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Only 14 data. That is not really enough to calculate the exact standard deviation, nor can you calculate the variable number, so that's just complete messed up statistics that results in a very large percentage error, 12% with 14 data.
In my point of view, if he says that there's 30 times in his experiment, then that's equals to a 4 times error in his 30 times experiment. So I would like the experiment to change into like 100 times in each degree, but if he only have a certain time to do this experiment, I would like the degree range to be bigger, but do more experiment on each degrees to give a better percentage error.
But in my opinion, I think the percentage error 12% is not that high because what we see is delta vertical velocity, and that is not. I think 12% is not. It's not that much because delta vertical velocity will be higher than just only when we measure the vertical velocity, and more we have the error bar, and we can see that it is inside the theoretical is inside error bar of the experimental data.
Can I please comment on this? Regarding that, you said that the delta V, right? Yeah, delta Vy. So you can consider it like this. So basically, we have a velocity right over here. This is just like a representation. It's not like the real thing. So we have the Vy, and we have the Vx. So we know that the V equals Vx squared plus Vy squared. And since this is considered in this, so this must be considered in this through the Pythagorean theorem. And since this affects the whole energy conversion, energy conservation theory, which is written right here as mentioned previously in my question segment, so this must be considered, and 12% is not an acceptable number.
Okay, so time is up. So scoring time. Okay, so please show your score for the report. reporter. 8, 7, 7, 7, 7, and 8. The second one for opponents. Please. 7, 5, 5, 6, 7, and 7. Finally, for reviewer. Okay, please show. 7, 6, 7, 8, 7, and 8. Thanks for everyone for this session. Please take break for 15 minutes.
What questions are on there? Oh, okay. Let's see. Team member addition challenges. Question 17. Hand a helicopter.
We reject.
Team erudition challenges. Question number 9. Light whiskers.
Okay, we.
No.
We accept.
Speakers are right on the name on the board.
I would like to start the presentation. Hello everyone. I'm the reporter from team S601 and we are going to present the problem number 9, the light viscosity. So this is the introduction. When a laser beam enters a soft film with a small angle, a rapidly changing pattern of thin branching light tracks may appear inside the film. Explain and investigate this phenomenon. So in this report, we are going to explain why the light will separate into the branches and investigate when the light will change the pattern on the surface of the bubble. This is the observation photo. As you can see, that this is the bubble film, and you can see the laser beam came in and it spread, but not the regular one. It turned into the few branches, like a broom, the tail of the broom. Okay. So first we need to define what the branching light is. So if there are at least 2 thin branches on whether left side or right side on the main light beam, we call it the branching light. Okay. So there's a main laser beam here, and there are two branches here, at least 2 branches. So the second, because it mentioned the angle in the problem statement, so we have to define what the angle is in the description of the phenomenon. So we find out that a soft bubble film there will have 2 definitions of the angle, and we need to find out we need to use what angles we are using. So the first angle is the light beam, is the angle between the light beam and the parallel surface. Parallel surface. And the other definitions of the angle is the angle between the tangent plane and the laser beam. So as you can see, the laser beam came in and touched this point at the bubble film, and this soft bubble, and this point has a tangent plate, and we decided to use this. We found that the other definition is the laser beam light and this tangent plane. Okay, the next one. So this is our theory. When waves or light pass through the interfering object, they will naturally scatter in all directions. As you can see, why the sky is blue, so this is the scatter of the light. So next. But when wave propagate, but when the light came into some special medium or wave enters some special medium, they will not scattering in all directions. They will turn into the branches like a flow of the river or during the mountain. Yes. So when waves propagating through a weak disordered potential with correlation length larger than the wavelength, produce surprisingly long narrow filaments. Instead of producing completely random speckle patterns, the slowly varying disordered potential gives rise to focused filaments that divide to form patterns resembling the branches of a tree. And this is a phenomenon. This phenomenon is called the branch flow. And this phenomenon is the branch flow of light. So for branch flow to occur, the median's random structure must be larger than the wavelength, and it has to be very smoothly in all directions. And the special feature of the soap bubble is that its thickness usually fluctuates between 5 nanometers and several microns, which causes the fluctuation of the refractive index between the liquid films, which just meets the requirement of the branch flow. When the thickness fluctuates within 1 to 2 wavelengths, the change in refractive index is quite significant, so that it causes the light deflection, and the result is the light turning to the branch flow. So we think that we need to find out when the light will just penetrate through a bubble, or the light will enter the soap film and become the branch flow. So we think that the light path is nearly the tangent of the bubble. The light will turn into the branches, not just penetrating it. Next. So a small arc of the bubble can be approximated as a flat. So according to next, can be approximated as a flat. So the light will go into the bubble film instead of just penetrating, because we know the bubble is very thin. Next. So this is our setup. This is a laser beam, and this is a bubble we created on a black plastic board. Next. So preliminary research, we find out that, look at this graph. The light will just penetrate in. There's no branch flow on the bubble film, and the other has it. So we cut the bubble into two flats. One is parallel to the plastic board, and the other is vertical to the plastic board, as shown below. So we want to find out when the bubble is. We want to find out the relationship between the laser beam and where the laser beam enters through a bubble, and what will it become. So our experiment. So this is a bubble film, and the light just penetrating here. And we see above, look at the top of the bubble, and there was no branch flow. And the results are the same. So we found out our last experiment of this flat is the light is nearly the tangent of the bubble, and we can see that the bubble actually, the laser beam actually turn into few branches, like here. Next. And this is a comparison with different bubble. The photos. So as you can see, the light turning to a branch flow is a tangent of the bubble. Yeah. So here, 2, 1, 2, 3, and more things. And so this is our comparison. So our next equation, we want to find out the parallel flat of the bubble. And this is still not happening in the French flow. And as you can see, when the laser beam is the tangent of the bubble, the branch flow appears here. And this is the comparison. And this is branch flow. So we found that in this first definition of the angles in the picture above it are nearly all the same. But the branching line only appears in some of them. So we use the second definition of the angle. So the definition is the angle between the laser beam and the tangent plane. So we want to find out, because in our theory we think that soap bubbles are fluctuating. And we want to verify it. So we use something is thick and thin and it's not flowing. And we want to compare with different angle of the light beam to verify our theory. So compare with a bubble and a plastic branch, because the pressure is very thin and it's not really fluctuating. And we found out that only the bubble, only the bubble soap bubble film has occurred with the branch flow, and the plastic wrap do not. So compared with different angle, we choose the tops of the bubble because it is convenient for our observation. Next, so this is nearly 90 degrees of the bubble between the laser beam between the tangent plane, and there are no branch flow. And the next is nearly the 60 degrees, and they're still not there still. And the other one, okay, and the next one below is it doesn't have two, and the last, so the next is still there, and the last one is nearly the tangent of the bubble, and it occurred the branch flow. Yes. So our conclusion is the branching line appears because of the fluctuation of the bubble's thickness. The branching line appears when only the light beam is nearly the tangent of the flow. So thanks everybody for listening.
Okay. So, how many questions to the topic?
Okay, hello. Could you please turn to page 4? I don't want to kind of log in slide. Page 4. Sorry. Okay. So, if there are at least two thin branches on whether the left side or right side, so would you consider this is the laser main line, right? So would you consider this as a branching line? Yes, this would be considered as a branching line. Yes. Would this be considered as a branching line? Okay. Second, please turn to page 7 of your presentation. Yeah, that's stuff right there. You said that this happens because there's some sort of special medium. Could you please define the term special medium?
And we just say for the branch flow to occur, the medium must be this curve.
Okay, that's fine. We can skip this question.
The median structure must be larger than the wavelet, and it has to be very smooth in all directions.
Okay. Okay. One last thing. You have like a slide, the thickness one, the one with the soap film thickness. Yeah, that one. So you're saying that thickness does affect this whole phenomenon? Yes.
Yes.
Okay. And one last one. For the soap bubble, do you have like a specific kind of like a concentration, the soap bubble? You have like a specific concentration. Is it like all the same throughout all the experiments? Is it the same concentration?
Oh yes, we have a special. We have a.
Okay, okay, thank you.
Okay, 3 minutes break.
还好吗？ Could you please close these lights? Yeah, yes. Something smells on the internet.
Okay. How many you can
Please, please. The thing. The thing.
No
It's
signal?
gone. It's dead.
Oh, okay, okay.
Okay. Okay, so I am from Team Revision, and this is our opponent report of question number 9, light blisters. Okay, let's check out the problem statement. It clearly states rapidly changing pattern, and so the key points I got was, the key point I got was, first of all, the mechanism of the changing lights, the branching lights, and the second, the certain conditions for these changing lights. Okay, so here's our brief review. For the observation photo, I'm not sure what to call that. The photo is quite high quality, it's pretty clear. Picture explanation was made, he did actually say what was happening in the picture, but cause it's not a video, we can't actually see what's happening there. And it doesn't really show the rapidly changing pattern which is mentioned in the problem statement, which I don't see what the point is. And for theory, concise graphics rather than lots of words. He doesn't read off the presentation, which is very good. Clear speaking, I could hear very clearly what he's saying from my seat. Repetitive speaking, constant repeat and stutter. He's not really familiar with his report. And there are no formulas, there are no physical or physics or mathematics equations to prove his assumption. I think that is a very, very big thing that he needs to fix. Now, the setup, it's concise, and you can simply assemble the experimental equipment, which is, it's not very expensive, but it's too concise. No one mentioned how these equipments are applied, nor the parameters of these equipment, such as the laser they use, the soap bubble they use. Nothing was said, and they did not know how to fix the laser beam angle. Okay, for the experiment, confident speaking, concise and clear slides are the same thing. Some pictures of the experiment are unclear. I'm not sure why, regarding that the observation photo was very clear. Did not consider certain parameters that may affect the phenomenon, especially ambient factors. Hard to compare the difference of experiment photos because of the typesetting of slides. You have like one there, one there, one there. It's not. This is messed up. Okay, conclusion. The reporter is pretty confident in speaking and designing the experiment with great creativity. However, there are like some small flaws that need to be considered and double-checked. And we would like to point out something. Many points regarding understanding of the report were skipped, such as in the theory part. This report is very lacking in mathematical and physical equations, which is necessary to make a theory complete. You need to let others believe what you are saying. Few parameters were discussed, resulting in avoidable blank spots in the report. You ignored too much of the ambient factors and the factors of your experiment itself. On the whole, okay, that's just weird. On the whole, it is a very interesting report, worth investigating. But if you just look at the details, it's heavily flawed and cannot be seen as one that is complete. Now, may I get into my discussion?
Okay, you can keep going.
Okay, first of all, in the question time, you mentioned that, oh yeah, it's this one. The thickness does matter, yes?
Yes.
How do you measure the thickness? How do you ensure the thickness is actually consistent?
Because the thickness is actually fluctuating, so we search in the internet the reference key that gave me the soap bubble film its thickness is usually fluctuating between 5 nanometers to several microns.
To what?
To several microns.
So micrometers, okay. Then how do you measure the actual thickness? Do you have like a mechanism that can regulate the whole? You can actually measure the thickness and then apply it into your theory. Do you have something like that? You discuss this parameter?
I need to measure the thickness of the bubble film?
No, I mean, do you discuss this parameter in your experiment, in your theory? Because you mentioned that thickness actually affects the whole phenomenon. Did you discuss this within your experiment?
Because each can you repeat your question again?
Did you or did you not consider the effect of thickness within your experiment? Did you or did you not?
No, because it is impossible for our high school students to measure the soap bubble film's thickness.
Okay. You mentioned that the soap bubble you use has a constant concentration. Am I right?
Yes.
What is it? You have like a specific formula or something like water to glycerin to detergent or something like that. Or what kind of soap did you use? Whatever.
They are very so it's the water and this is a soap film
or dishwasher.
And we use the same dishwasher. So.
Okay.
And the other thing, I can't speak English, but I can show you the
glycerin.
Glycerin.
Okay. what? Did you consider this as a possible parameter that you can change as a considerable factor throughout the experiment?
Actually, we tried many different formula, but many of them is not quite stable on the plastic board. So we choose this because it's the most stable one.
So you did not consider the fact that you could have put this into account and
I consider it, but it just pop out when it falls on the film. So I think we have to we find out that the one which not will pop out on the film.
What's the temperature of the soap water?
Soap water.
Yes, the temperature.
25
degrees Celsius. What's the room temperature? Is it constant? The ambient temperature of the whole, the whole room, is it constant?
Yes.
It is. How much is it?
25.
Oh, so it's the same. Oh, that's interesting. Did you conduct any error deviations? Because I certainly did not see any within your report. Did you conduct any data? Did you conduct any deviations of errors and analysis? Oh my God, analysis of the data. Did you conduct anything? Yes.
What kind of the number you want me to?
Experimental data, anything. Because I didn't see anything.
We didn't actually. We do many types of experiments, but we just collect some of them to do the report. But sorry, I didn't collect it into like
A graph. You did not collect all of the. Define many. You said you did many experiments. How many did you do?
Every single angle for 10 times.
Every single angle.
This time we do we did 10 times, and this one we did 10 times.
So you had 20 times of experiments.
Every line.
How many angles did you use?
How many angles?
Are there any others that were not mentioned in this report?
You mean what?
The angle in which you shot the laser at the bubble. How many kinds of angles? How many different angles did you use? 10 degrees, 20 degrees? How many?
My English isn't very well, so I use nearly 30 degrees because it's and 45 and 60 and 90. And there may be some more because it's not. There may be some more of them, but I just ignore it because it's not. Because it haven't appeared the branch flow and it has.
So you're telling me you're ignoring the ones that cannot emit, they cannot be presenting this phenomenon, which is to be considered in the problem statement to consider the relevant parameter.
But it is still fit of zero, which is tangent.
Okay, did you measure the maximum angle at least in which when you shoot the laser at the bubble, the phenomena will appear? Did you measure the maximum and minimum angle?
Sorry, I didn't measure it because it is hard to measure that the soap bubble and it is very hard to measure, and this will not appear from any and it's too hard to measure. And
okay, here's my suggestion. What if you put for example, the bubble was here, and you're shooting the laser from this direction. What if you put a camera right here and actually shot the angle? You actually took a picture of the angle in which the maximum and the minimum, in which the phenomenon is actually occurring. What if you analyze these pictures with, I don't know, some kind
but
of
if you shoot it here, you will just appear a little dot.
Your picture would look like this because you're shooting an angle from right here. So then you could have a x-axis as a horizontal, the horizontal axis, and then you can measure the theta or phi or whatever you call it. You can measure the angle from there.
But in the picture, you will just see a soap bubble here, and with the laser beam here, and a green dot here.
No, I mean, no. See, if this is the bubble, I know it doesn't look like a bubble, but if this is the bubble,
yes.
And assume the laser is shooting from here.
Yes.
You're shooting the camera from this direction. You're shooting the camera from this direction.
Yes, I should.
Yes. So you could potentially measure the angle in which the maximum and the minimum. You could potentially do that. potentially, if you have the proper equipment. Oh yeah, machine equipment. What kind of laser did you use?
I use it, you mean the wavelength of this or?
The relevant parameters, the wavelength, the watts, the strength, whatever.
I forget the watts, but I can tell you the wavelength is 532 nanometers.
532 nanometers. Okay. Okay. Why did you choose that laser? Why? 532 nanometers. Is that a special number or something?
Because it's the most common wavelength of the green light laser.
Did you consider the possibility in which when you change the wavelength of the laser itself, it could possibly affect the phenomenon?
I think it will still appear the principle, but it's not quite. I don't understand what you mean.
I mean, if you change the wavelength of your laser, it could possibly, potentially affect the phenomenon itself. What pattern does it show? Like the pattern of the branches, what does it show? It may affect your experimental results. Have you ever considered this as a potential parameter? You can use?
I did consider it,
but you didn't do it.
Yes, because
speaking
of the rapidly changing temperature, I have some video. I have a video of the.
But you didn't put it on the report.
I
Are you going to show me now?
I put it in the backup page.
Okay, go ahead, please.
43. Hey. Here. And sorry, it's crying out.
There's nothing. It's just a dot.
Here.
Okay.
Here's a changing pattern of the trench flow here. You can see it.
Okay. At what degree is this going in? What angle is this going in to the soap bubble?
I didn't measure it because it was for the observation.
So this is a different thing from your experiment. This was not shot during your experiment.
Yes, this is not shot during our experiment.
Okay. Okay, that's pretty much it. Thank you.
Okay. Summarize.
Summarization. Okay, as we can see, the reporter ignored many of the considerable parameters, such as the wavelength of the laser, the thickness of the bubble, and has failed to develop a method in which you can actually measure the thickness of the bubble, which can be done through certain theories that I have discovered. The experiment with the video, that's weird. I mean, why don't you just shoot the experiment video when you're doing the experiment? That makes no sense at all and it just doesn't make sense. And when he doesn't know what angle in which that is shot, and he basically this report is a mess. That's what I'm saying. Thank you.
Okay, reviewer. Okay.
First of all, for the reporter, what is the radius of your laser beam?
Laser beam. Sorry, I didn't measure it.
Do you know the intensity of your laser beam?
I didn't measure it.
Okay, next thing, did you control the humidity? Do you control the humidity when you're doing the experiment?
In the same room which is inside the building.
Okay. For the opponent, do you think that the previously mentioned three parameters can affect the pattern?
What parameters? Specify.
The radius of the laser beam, the intensity of the laser beam, and also the humidity of the environment.
Well, of course, the humidity will affect the bubble's thickness itself, and as said in the report, it does affect the phenomenon at the lasers.
Thank you.
Okay.
The next question is, do you consider the change of thickness and over time?
What do you mean?
The bubble's thickness.
The bubble's thickness during. Yes, it will change during the experiment.
Okay.
And
the next question is, do you have imagination of how can you
quantify your data?
Okay, I found it. I probably can measure more angles of the.
I mean quantify of your
fringe.
That's how.
Because it's a render, and so I didn't think the way to measure it quantify.
Okay. For opponent, do you have any idea how to quantify the data?
You mean the data in which we measure things?
For example, from
the thickness of the.
No. He showed pictures, right?
Mm-hmm.
So, is there any way to make that picture into something like a chart or a plot or something?
Of course, we can measure the angle and then measure when the light comes out, right? You shoot the laser and it goes into the bubble and it comes out of the bubble. You can measure that, the light that comes out of the bubble. You can measure that, the wavelength of it, and then you can, through thin film interference theory, you can get the thickness of the bubble film. So we can measure at what degree, at what thickness of the bubble film.
Thank you. The next question is, do you think the viscosity of the bubble will affect the results? For example, I believe you put glycerol.
Yes.
What's up?
Well, I think maybe it's a parameter, but I didn't imagine how it affect the result.
Okay. Thank you.
Okay, 2 minutes break.
Honorable jurors and distinguished competitors, I'm Chen Liangyu from Team Lagrangian. Today, I'm reviewing problem number 9, light whiskers. As the problem statement stated, when a laser beam enters a soap film at a small angle, a rapidly changing thin fringe light tracks may appear inside the film. Investigate this phenomenon. So the focus for this problem should be how does the rapid changing pattern behave, and how does the laser beam propagate in this film? And also, the problem statement mentioned a small angle. So the limitations for this phenomenon to happen should also be investigated as well. Moving on to the reporter's performance, we can see he presented his phenomena. He recreated his phenomena, but did not present the part when the patterns are rapidly changing. For the theory part, they said they have mentioned a scatter of light, branch flow, and fluctuation of bubble thickness. But however, they did not give any quantitative formulas or equations to describe the phenomena. And for the experiment part, in our opinion, they are only observations, and they have a lack of data. Moving on to the pros and cons of the reporter.
they read the reference to obtain a qualitative theory, and their pictures for the experiments are clear. However, they have a lack of quantitative theory and qualified data. And they also have poor time management as their presentation speed up intensely at the end of their presentation. And they fail to fulfill the problem statement by not investigating the angle boundary for which the phenomena will happen. And they did not investigate the rapid changing of the pattern inside the soap film. Next, for the opponent's performance, in the presentation part, they point out that the reporter's theory does not have a formula. And they also point out that the experiment setup may not be stable enough. And the presentation used a lot of photos to represent data is hard to read. And the pros are the opponent asks sharp questions and used the blackboard to present his ideas clearly and discuss some of the relevant parameters. However, the cons are he didn't discuss enough on the changing pattern inside the film, and he didn't provide a viable suggestion to quantify his data. So moving on to the discussions, first of all, they discuss about how to fix the thickness of the film, and the reporter gave a range based on the reference, and he's unable to measure it. And we think that it's fluctuating over time, so it should be discussed in a statistical way. And also, they measured the angle boundary, and the opponent asked if he measured it, and the reporter said it's too hard to measure. And we agree with the opponent that we can measure it with a camera. And other discussion points during this discussion are the soap film formula, the temperature, the experiment, how many times they've done the experiment, the wavelength, angle, and branches. These are some points that we think they missed. First of all, the intensity of the laser and the thickness of the laser beam. And the construction and the soap film property over time is also not mentioned. And they did not give a...
Okay, time is up. Thanks. Okay, finally, reporter have 2 minutes for conclusion.
This is my time to concluding the report. So I think that my report I think that the opponent and the reviewer gave some many good advice to tell me what parameter to do in the future, but they didn't give something available to quantify the result of the experiment. They just say you need to quantify it, but they didn't say how to quantify it. And the third question is the temperature of the salt water and room are fixed. Yes, it's both 25 degrees Celsius because we do it in the same room and we put all our equipment in it. And why did you choose the laser beam used in the experiment? We use it because it is 532, which is the usual wavelength of the green light. We do acknowledge that there are many flaws in the report, and we could make the improvements such as quantifying, and as we have done the experiment under fixed conditions. We believe that the environmental can be ignored during our experiment, but there are all possible parameters to consider in the future. Thank you.
Okay. So it's time for the question of jury. Any questions for our jury? Okay.
Will any of you offer me a physical reason why we see this branching effect?
Yes, I can. Like for instance, there's something called caustics. It is caused by an uneven thickness of the soap film, causing an uneven surface between those two thicknesses. And when two beams of light reflect out of the thickness, the thicker one, it passes through the uneven surface and creates what we call a refraction. So that creates a darker one and a light and a one that is more visible. So, and they have different angles depending on the horizontal angle. So what we can see is that you have more clearer rays, and then there are these darker rays, all shooting out from different angles, and this is caused by caustics.
Sorry. So your explanation.
In my explanation is that the same of the reviewer, because the sum of the thickness of the soap bubble is not even because it is usually fluctuating. So
why didn't you say it in your report?
What?
Why didn't you explain what you just said in your report?
I did explain the during my report. I just didn't type it in the.
Basically, the idea is the same because of the difference in refractive index. But one important point is that the laser beam have a thickness. So inside this, let's say the width of the laser beam, there are different refractive index. So it branches out instead of refracting the same way.
So the opponent and the reviewer all emphasize the important so-called rapid change pattern of laser, right?
Yes.
So,
yes.
But your explanation, how do you relate to this condition to the explanation you just tell us?
So
it seems that if you use the stable laser, still they have such a phenomenon, right?
I believe that the bubble, the surface of the soap film is flowing. So even though the laser didn't change position, the soap film itself is changing the refractive index at, for example, the same point.
And I believe that the thickness, also as the reviewer just said, the thickness of the soap film changes and is not distributed evenly throughout the whole bubble, whether it is a flat soap film or a convex soap film like a bubble thing. So it creates uneven surfaces with certain patterns that may create rapidly changing phenomenons described in the problem statement.
So both of you assert that even without a rapid change of laser, you still have this phenomenon or not?
Yes.
Do you need it? Do you need a rapid changing pattern of light?
I'm sorry, could you ask the question again?
So, according to what you said, it seems for me that you don't need a rapid pattern of the light to create this phenomenon at all. As long as I have an even film, that's enough, right?
I need an uneven and rapid changing film.
Why?
Because the phenomena is caused by the uneven film, and the changing pattern is because of the changing of the film.
I think that the light could be discussed, like the laser's radius, the laser's wavelength, they may cause different patterns, but what's really motivating this phenomenon itself is what I've just previously mentioned, caustics, because like the two uneven surfaces, it causes different refractive indices and causes differentiate reflection that create darker ones, lighter ones, and all different kinds of patterns. That's what really is pushing this phenomenon.
A question for three of you. So you all mentioned laser, and then the reporter used a green light laser, 32 nanometer laser. And I just want you to imagine, so what if you use a different laser, I mean a different wavelength, even different power, and what's the qualitative change of the experiments? Not the quantitative, qualitative.
The qualitative change, the phenomenon.
Or no, you can just answer no if you have.
I think the branching phenomena will be changed, like more branch or less branch.
it would definitely look different depending on the wavelength, since the wavelength directly correlates to thin surface interference, which can be used to measure the thickness of the soap film. So that would definitely affect the way that you're doing your experiment. And the radius at which the laser is shot definitely affects.
I think the difference between the maybe the red light laser or the other line of laser, maybe it will change its distance between the first branches appear, maybe because its thickness, its wavelength isn't the same with the green light laser.
Okay. No more questions. This was our scoring time. Please. Okay. So please show the score for the reporter. 6, 6, 4, 4, 4, and 4. The second one for the applicant. Please. 7, 9, 9, 8, 6, and 9.
Thank you very much.
Finally, for the reviewer, please. 8, 8, 8, 8, 7, and 8. Thank you for in this morning section.